This video is brought to you by ioMosaic Corporation leaders in providing process safety guidance to the process industry. This video and any information contained within this video is copyrighted, proprietary and confidential in nature, belonging exclusively to ioMosaic Corporation. Any reproduction, circulation, or redistribution is strictly prohibited without explicit written permission of ioMosaic Corporation. This video paper on quantifying non-equilibrium flow and rapid phase transitions is brought to you by Georges Melhem and Greg Hendrickson. Rapid phase transitions, RPT. A fluid can also be made metastable by rapid heating or rapid cooling at constant pressure, as shown in Figure 1, by going from point C to D, rapid cooling, or by going from point D to C, rapid heating. In the case of extremely rapid cooling, a vapor will have to condense and partially or fully convert to liquid when it crosses the vapor thermodynamic stability limit. Under rapid heating, a liquid will have to generate vapor when it crosses the thermodynamic stability limit for liquid as it usually experiences in liquefied natural gas, LNG, rapid phase transitions, or steam explosions. Figure 2 illustrates how an LNG mixture can be rapidly heated to the superheat limit at ambient pressure, causing a rapid phase transition. A rapid phase transition is the very rapid, near spontaneous, generation of vapor as the cold LNG is vaporized from heat gained from the underlying spill surface or from large volumes of water contacting LNG in a storage tank. Because the vapor is evolved very rapidly, localized overpressure is created. This is also sometimes described as a physical explosion. Following a release of LNG from a ship or storage tank, a liquid pool forms and spreads on the surrounding spill surface. Rapid phase transitions have been shown to occur during or following an LNG spill. The hazard potential of rapid phase transitions can be severe, but is highly localized within or in the immediate vicinity of the spill area. Prediction of RPT hazard potential. Rapid phase transitions are also referred to as physical explosions. This type of explosion does not involve combustion or a chemical reaction to create mechanical explosion energy. Instead, mechanical or explosion energy is created from the rapid expansion of a high-pressure metastable fluid to ambient pressure. As illustrated in Figure 1, a liquid can be made thermodynamically unstable, metastable, by rapidly changing its temperature and pressure such that it cannot exist at those conditions in its initial state, all liquid. Even during very rapid heating or very rapid depressuring, all fluids must change phase ultimately. These phase change limits, also called the thermodynamic stability limits, can be determined accurately using an equation of state. An LNG rapid phase transition can be explained using the thermodynamic stability limit, also called the superheat limit. We illustrate the rapid heating process of LNG leading to a rapid phase transition on a phase diagram. LNG consists predominantly of methane. Certainly, LNG compositions will contain higher fractions of ethane and some propane, and as a result, their phase diagram is different from that of pure methane. First, let us look at how the superheat limit is reached for pure liquid methane. This is illustrated graphically in Figure 6. Follow the dashed blue line at the bottom of Figure 6. Pure liquid methane boils at 111.6 Kelvin, negative 258.8 degrees Fahrenheit, at ambient pressure. Rapid heating at ambient pressure causes methane to reach the thermodynamic stability limit of 171.4 Kelvin, negative 151.15 degrees Fahrenheit. Once heated to that temperature, methane becomes a superheated liquid, i.e., a saturated liquid with a vapor pressure of 24.6 bars. Methane reaches the superheated state and has to give up its superheat by expanding because the ambient pressure is 1 bar. If we assume the expansion process is reversible, or isentropic, we can bring methane back to its superheated state by adding back the same amount of energy it lost when it expanded. Methane will expand to 1 bar and exert 56.2 kilojoules per kilogram in mechanical work, physical or pressure volume, or energy on the surroundings that can be used to create overpressure, i.e. explosion energy. In reality, the expansion process is not reversible, and its efficiency at best is around 50%, as established by actual testing. This is because the expansion process loses energy as it creates turbulence and as the liquid flashes to vapor. As a result, the maximum possible rapid phase pressure that methane can reach is 24.6 bars, and its mechanical explosion energy is 28.1 kilojoules per kilogram. This is equivalent to burning 0.56 grams of methane vapor. In other words, on per unit mass basis, the methane combustion process produces 1,780 times more energy than a rapid phase transition. This is why, historically, rapid phase transition overpressure estimates were excluded from LNG risk assessments and considered to be negligible and localized. Now let's repeat the same process for an LNG mixture. An LNG mixture containing high fractions of ethane and propane is more likely to undergo a rapid phase transition than pure methane. This is observed in real LNG spills and can also be proven theoretically. Instead of a vapor pressure curve, an LNG mixture has a phase envelope consisting of a bubble point curve and a dew point curve as illustrated in Figure 2. Follow the dashed blue line at the bottom of Figure 2. This LNG mixture boils at 115.8 Kelvin at ambient pressure. Rapid heating at ambient pressure causes the LNG mixture to reach the thermodynamic stability limit of 191.4 Kelvin. Once heated to that temperature, the LNG mixture becomes a superheated liquid, i.e. a saturated liquid with a bubble point pressure of 36.0 bars. The LNG mixture reaches the superheated state and has to give up its superheat by expanding because the ambient pressure is 1 bar. If we assume that the expansion process is reversible, or isentropic, the LNG mixture will expand to 1 bar and exert 75.5 kilojoule per kilogram in mechanical work or energy that can be used to create overpressure, i.e. explosion energy. As mentioned earlier, the expansion process is not reversible, and its efficiency at best is around 50%. As a result, the maximum possible rapid phase pressure that the LNG mixture can reach is 36.0 bars, and its mechanical explosion energy is 37.75 kilojoule per kilogram. An LNG mixture rapid phase transition produces 1,325 times less overpressure energy per unit mass than the combustion process. The explosion energy predicted by the superheat limit at 37.75 kilojoule per kilogram, or 20.7 kilojoule per litre, is consistent with recent spill data measured by Shell at 5.6 kilojoule per litre. Until a more detailed model is developed to better represent the rapid phase transition process, we recommend the use of the superheat limit explosion yield of 20.7 kilojoule per litre. This number can easily be established for other LNG compositions of interest. Although not recommended by the authors, the explosion yield of 20.7 kJ per litre can be used with a simple TNT equivalency method to predict overpressure contours from a rapid phase transition with a specified amount of LNG. Note that TNT equivalence will overpredict near-field overpressure values and is therefore considered to be a conservative method. Even if we were to consider the physically impossible, for example, the entire contents of one LNG storage tank, say 25,000 metres cubed, participated in a single RPT at the same time, only a small portion of the liquid spilled on water that is in intimate contact with the spill surface has been shown to participate in an RPT in large-scale field trials. The overpressure hazard radius to 1.0 psi would be estimated at 0.82 miles from the centre of the RPT. The RPT hazard radius is well within distances of concern of LNG flammable dispersion to 1/2 LFL for releases from hole sizes ranging from 1 to 5 metres. Predicting RPTs from LNG spills. Existing modelling methods fall short from being able to identify with accuracy what fraction of an LNG spill will participate in a rapid phase transition. However, there are existing advanced modelling techniques that can tell us if a rapid phase transition will occur and at what approximate time during the spill it will occur. Before discussing RPT modelling, one needs to understand the different boiling regimes based on the temperature difference between the heating surface and the liquid. Figure 7 illustrates the various boiling regimes for LNG and nitrogen spills. The process of forming vapour in all liquids, also referred to as flashing, usually involves what is called nucleation sites. For example, in a process vessel, these nucleation sites can be small imperfections on the vessel inner surface, or tiny colloidal suspensions of dirt or dissolved gas in the liquid. Nucleation is a process where vapour bubbles start to form in these surface imperfections when a liquid is heated to a boiling state. The nucleation process requires mass and heat transfer in order to produce vapour. If heating occurs at an extremely rapid rate, these nucleation sites are rendered inactive as they do not have enough time to complete the mass and energy transfer or exchange required to generate the vapour bubbles, for example, nucleate. The same effect can be produced by dropping the pressure of a saturated fluid very fast, as shown in Figure 1. When LNG is spilled on land or water, LNG is initially very cold, 110 Kelvin or negative 261.67 degrees Fahrenheit. The spill surface, land or water, is initially very hot compared to the temperature of LNG. Even cold ocean water is typically around 60 degrees Fahrenheit or 289 Kelvin. The initial difference between the LNG and the water surface is 289 minus 110 or 179 Kelvin, 322 degrees Fahrenheit. This high temperature difference causes the LNG to start boiling. Because the difference in temperature is so high initially, a vapour film is formed at the contact point between the LNG and the underlying spill surface. See Figure 7. This vapour film will persist until the spill surface cools enough and/or until the LNG bubble point temperature gets high enough as methane is preferentially depleted from the liquid LNG spill. As long as the vapour film exists between the LNG and the spill surface, heat transfer is greatly reduced. Vapour layer acts as an insulator also. When the difference in temperature between the LNG and the spill surface gets smaller, the vapour film is destroyed and a different, faster heat transfer mode begins. The rate of heat exchange between the cold LNG and the warmer spill surface is now orders of magnitude larger than it was with the vapour film intact. As a result, the LNG is heated very rapidly, almost instantaneously, to the superheat limit, and a rapid phase transition occurs.